the probability of the walk being a success and the probability of it being a failure are actually very small. They're both in the order of n to the minus 1/3, so most walks are small. But if you condition on the fact that a certain walk was not small, then there is a probability that it's a success. It may be small, depending on what those numbers are, but it's positive, which is enough. So the thing that we still have to do here is to show that there is a positive probability that some walk that starts in this interval is not small. And the way that we're going to do that is we're going to think about the number of small walks that can start in that interval. So that number is either big or small. And again, we say that many small walks is more than a n to the 1/3, where a is some number that can be optimized. But the thing is that even though most walks are small, if you ask for too many consecutive small walks, then the probability that that happens becomes small. And on the other hand, if you have few small walks, then the probability that they are enough to get to the end of the interval is also small. So by choosing a good place to call, few walks, many walks, then maybe those two probabilities can be small enough at the same time that we get to say that there is something starting in there that is not small. So that's what's happening. The probability of having many small walks is going to 0 as alpha goes to infinity. If we choose, depending on what we choose A to be, I guess. A has to be something, all the numbers have to be chosen such that some alpha cubed shows up in that exponent. And on the other hand, the expected size of one walk is like epsilon to the minus 1, so it's n to the 1/3. When we take n to the 1/3 walks together, the expected value is in the order of n to the 2/3, which is the same scale as the interval size that we're looking at. But depending on the numbers that you choose, you can make it so that the probability of it being more than the interval is small. So yeah, that works. So I don't have really much time to talk about the other two bounds, but let me just say a couple of words about each of them. For the upper bound on the left side, we're using a bigger process and just asking for the probability that it gets to half of the distance from there to n without crashing. So if the last crash was before here, then in particular there is no crash between here and there, and also no crash in a bigger process. And for the lower bound on the right side, again we use a bigger process, and we actually look at it starting at some place before n, because we don't really have enough good-looking formulas for the height of a process on that side. The fact that the fixed parameter one can go to infinity really makes it hard to look at. But this is enough, and all of them turn out to be something like e to the minus alpha cubed. So the picture for the histogram, the picture for the distribution that we had is actually what it should look like. This is the distribution of the place of the last crash.